For over 300 years, we believed gravity was instantaneous, that if the sun suddenly vanished, Earth would immediately fly off into space. Then Einstein came along and shattered this certainty, proposing that nothing, not even gravity, could travel faster than light. But here's what will blow your mind. Recent observations of colliding black holes and neutron stars have finally answered this ancient question in ways that challenge everything we thought we knew about the fabric of reality itself. Today, you're about to discover whether gravity truly obeys the cosmic speed limit, or if it somehow transcends the very laws that govern the universe. If you're fascinated by the fundamental forces that shape our cosmos, make sure to subscribe to this channel and give a thumbs up. I am just starting my journey on YouTube, and your support means a lot to me as we explore these cosmic mysteries together. One quick question. If you could instantly master any scientific field, which would you choose? Astronomy, quantum physics, or something else? And tell me why on the comments down below. I will choose the most creative answer. Now let's begin. The story of gravity's speed begins with Isaac Newton, who in 1687 published his law of universal gravitation. In Newton's universe, gravity was a force that acted instantaneously across any distance. If the sun disappeared, Earth would immediately feel the loss of gravitational pull and fly off tangentially into space. This instant action at a distance troubled even Newton himself, who admitted he couldn't explain how it worked, only that it did. For over 2 centuries, this instantaneous gravity was accepted as fact. Astronomers used Newton's equations to predict planetary orbits with stunning accuracy. They discovered Neptune by observing gravitational perturbations in Uranus's orbit. Everything seemed to work perfectly. But there was a problem lurking in Mercury's orbit, a tiny discrepancy that would eventually lead to a complete revolution in our understanding of gravity and its speed. Mercury's perihelion, the point where it's closest to the Sun, advances by 43 arc-seconds per century, more than Newton's laws predict. This might seem trivial, but it was a crack in the foundation of classical physics. Astronomers searched for an unseen planet called Vulcan that might explain the anomaly, but it didn't exist. The answer would come from a patent clerk in Switzerland who dared to reimagine space and time themselves. In 1915, Albert Einstein published his general theory of relativity, which completely reimagined gravity not as a force, but as the curvature of space-time itself. Mass and energy bend the fabric of space and time, and objects follow the straightest possible paths through this curved geometry. But crucially, Einstein's theory predicted that changes in gravitational fields propagate at exactly the speed of light, 299,792,458 meters per second. This was a radical departure from Newton's instant gravity. If Einstein was right, when the sun disappeared, Earth would continue orbiting the empty space for 8 minutes and 20 seconds. The time it takes light to travel from the sun to Earth. We would see the sun vanish and feel the loss of gravity at exactly the same moment. But how could we test this? We can't make the sun disappear, and until recently we had no way to directly measure gravity's speed. The first indirect evidence came from studying binary pulsars, pairs of neutron stars orbiting each other. The Hulse-Taylor binary pulsar, discovered in 1974, provided a natural laboratory for testing Einstein's predictions. These incredibly dense objects, each containing more mass than our Sun, compressed into a sphere just 20 kilometers across, orbit each other every 7.75 hours. Dr. Joseph Taylor and Dr. Russell Hulse, who won the Nobel Prize for this discovery, spent years timing the pulsar's radio pulses with microsecond precision. They found that the orbit was decaying exactly as Einstein predicted if the system was losing energy through gravitational radiation traveling at light speed. The pulsars were spiraling together at precisely the rate expected if gravitational waves carried away energy at the speed of light. But this was still indirect evidence. The smoking gun would come from directly detecting gravitational waves and measuring their speed. This seemed impossible. Einstein himself doubted we would ever detect the incredibly tiny distortions in spacetime that gravitational waves produce. It would take a century of technological advancement and one of the most precise instruments ever built to finally answer the question. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, consists of two facilities, one in Louisiana and one in Washington State. Each detector has two 4-kilometer-long arms arranged in an L shape. Laser beams bounce between mirrors at the ends of these arms, and gravitational waves passing through cause tiny changes in the arm lengths, changes smaller than 1/10,000th the width of a proton. On September 14, 2015, LIGO made history by detecting gravitational waves from two black holes merging 1.3 billion light-years away. The black holes, 29 and 36 times the mass of our Sun, spiraled together and merged in a fraction of a second, converting 3 solar masses into pure gravitational wave energy. The waves traveled across the universe for over 1 billion years before reaching Earth. The signal arrived at the Louisiana detector, then 7 milliseconds later at the Washington detector. This time delay, corresponding to the light travel time between the detectors, immediately told us that gravitational waves travel at the speed of light, not faster or slower. But scientists wanted more precise measurements before declaring the question definitively answered. The game changer came on August 17, 2017. LIGO and the European Virgo detector observed gravitational waves from two neutron stars colliding 130 million light-years away in the galaxy NGC 4993. But this time, something extraordinary happened. Telescopes also saw the event. NASA's Fermi Gamma Ray Space Telescope detected a gamma-ray burst from the same location just 1.7 seconds after the gravitational waves arrived. Think about what this means. The gravitational waves and light traveled together across 130 million light-years, a distance so vast it takes light over 100 million years to traverse. Yet they arrived within 1.7 seconds of each other. Given the uncertainties in exactly when the gamma rays were produced relative to the merger, this confirmed that gravity travels at the same speed as light to within 1 part in a quadrillion. Dr. David Reitzer, executive director of LIGO, called it a discovery of a generation. We had finally answered a question that had puzzled humanity since Newton. Gravity travels at exactly the speed of light, not a fraction faster or slower. Einstein's prediction, made a century earlier based purely on theoretical considerations, was spectacularly confirmed. But why should gravity travel at light speed? The answer lies in the fundamental structure of space-time itself. In Einstein's theory, the speed of light isn't really about light. It's the maximum speed at which cause and effect can propagate through the universe. It's the speed of causality itself, the cosmic speed limit that preserves the logical order of events. And if you want to dive even deeper into the mysteries of gravity, black holes, and the speed of light, I highly recommend the book called Black Holes and Time Warps: Einstein's Outrageous Legacy by Kip Thorne. It's a fascinating, popular science book that brings the story of gravity and relativity to life, from Newton and Einstein to the latest discoveries in gravitational waves. You'll find the link in the description. Electromagnetic waves travel at this speed because photons are massless. Gravitational waves travel at this speed because gravitons, the hypothetical quantum particles of gravity, are also predicted to be massless. Any massless particle or wave must travel at exactly this cosmic speed limit, neither faster nor slower. It's not that light and gravity happen to travel at the same speed. They both travel at the fundamental speed of spacetime itself. The detection of gravitational waves traveling at light speed wasn't just a confirmation of Einstein's theory. It was a watershed moment that transformed our entire understanding of the universe. To truly grasp the significance of this discovery, we need to journey back to that extraordinary day in August 2017 when humanity witnessed something that had never been seen before: the collision of two neutron stars observed in both gravitational waves and light, definitively proving that gravity propagates at the speed of light. The event, designated GW170817, began 130 million years ago when two neutron stars in their final death spiral finally touched. These weren't ordinary stars. Each was the ultra-dense remnant of a massive star that had exploded as a supernova containing more mass than our Sun, compressed into a sphere just 20 kilometers across. For millions of years, they had been orbiting each other, slowly spiraling inward as gravitational waves carried away their orbital energy. In the final seconds before collision, they were orbiting each other hundreds of times per second, moving at significant fractions of the speed of light. The gravitational waves they produced grew stronger and stronger, reaching a crescendo as the neutron stars finally merged. The collision was so violent it literally shook the fabric of spacetime, sending ripples spreading outward at the speed of light. 130 million years later, on August 17, 2017, at 12:41 and 4 seconds UTC, these gravitational waves reached Earth. The LIGO detector in Louisiana registered the signal first, followed by the detector in Washington State 8.5 milliseconds later, with the Virgo detector in Italy confirming the detection. The signal lasted about 100 seconds, rising in frequency from 35 Hz to over 2000 Hz as the neutron stars spiraled faster and faster. But here's where it gets extraordinary. Just 1.74 seconds after the gravitational waves were detected, NASA's Fermi Gamma Ray Space Telescope observed a short gamma-ray burst from the same region of sky. The European Integral Satellite confirmed the detection. Within hours, optical telescopes around the world and in space had swung toward the source, locating a new point of light in the galaxy NGC 4993. Dr. Franz Cordova, then director of the National Science Foundation, called it an unprecedented discovery. For the first time in history, we had observed a cosmic event through both gravitational waves and electromagnetic radiation. But more importantly for our question about gravity's speed, we had two different types of signals that had traveled the same distance, 130 million light-years, and arrived almost simultaneously. The precision of this measurement is staggering. The gravitational waves and gamma rays traveled for 130 million years, yet arrived within 1.74 seconds of each other. That means their speeds match to within 1 part in 10 to the 15th. That's like measuring the distance from Earth to the Sun and being accurate to within the width of a human hair. This extraordinary precision definitively proved that gravity travels at the speed of light. Dr. Daniel Holtz at the University of Chicago, who was part of the discovery team, explained the significance. We've been wondering about the speed of gravity for over 300 years. Newton thought it was infinite. Einstein said it was the speed of light. And now we've proven Einstein right, with incredible precision. It's one of those fundamental questions about the universe that we can finally answer. But why did it take us so long to measure something so fundamental? The answer lies in the incredible weakness of gravitational waves. When those neutron stars collided 130 million light-years away, they released more energy in gravitational waves than all the stars in the observable universe combined. Yet by the time these waves reached Earth, they stretched and compressed space by less than 1/10,000th the diameter of a proton. Detecting such tiny distortions required some of the most precise instruments ever built. The LIGO detectors use laser interferometry to measure these microscopic changes in distance. A laser beam is split and sent down two perpendicular 4-kilometer arms. The beams bounce off mirrors at the ends and recombine at the detector. Normally, the beams cancel each other out. But when a gravitational wave passes through, it stretches one arm while compressing the other, causing the beams to go slightly out of phase and creating an interference pattern. The sensitivity required is almost beyond comprehension. LIGO can detect changes in distance smaller than 1/10,000th the diameter of a proton over a 4-kilometer distance. That's like measuring the distance to the nearest star with an accuracy better than the width of a human hair. The mirrors are suspended on glass fibers thinner than a human hair, isolated from all vibrations. The laser beam tubes are maintained at a better vacuum than interplanetary space. Dr. Rainer Weiss, who conceived of LIGO in the 1970s and won the Nobel Prize for its success, spent decades overcoming seemingly impossible technical challenges. Every truck driving by, every wave crashing on a beach hundreds of miles away, even quantum fluctuations in the laser light itself, all of these create noise that could drown out gravitational wave signals, he explained. The fact that we can detect space-time distortions smaller than an atomic nucleus is a testament to human ingenuity. The confirmation that gravity travels at light speed has profound implications for our understanding of the universe. It means that if the sun suddenly disappeared, we wouldn't know for 8 minutes and 20 seconds, the time it takes light, and now we know gravity, to travel from the sun to Earth. We would continue to see the sun and feel its gravitational pull for those 8 minutes, orbiting a star that no longer exists. This finite speed of gravity has observable consequences throughout the cosmos. When we observe the planets in our solar system, we see them not where they are now, but where they were when the light left them. Similarly, we feel their gravitational pull not from where they are now, but from where they were when the gravitational influence left them traveling at light speed. For nearby objects, this delay is tiny, just over a second for the Moon, minutes for the planets. But for distant objects, the delay becomes significant. Dr. Clifford Will at the University of Florida, one of the world's experts on testing general relativity, points out that this creates a subtle effect called gravitational aberration. When Earth orbits the Sun, it's not pulled directly toward where the Sun appears to be, but toward where the Sun actually is, accounting for the light travel time. General relativity predicts this perfectly, and observations confirm it to extraordinary precision. The speed of gravity also explains why binary pulsars lose energy and spiral together. As they orbit, the changing gravitational field propagates outward at light speed, carrying away energy in the form of gravitational waves. This energy loss causes the orbit to decay, bringing the pulsars closer together. The Hulse-Taylor pulsar has been observed for over 40 years, and its orbital decay matches Einstein's predictions to better than 0.2%. But perhaps the most profound implication is what this tells us about the nature of space-time itself. The fact that both electromagnetic and gravitational waves travel at exactly the same speed suggests they're both manifestations of something deeper, the fundamental structure of space-time. Light speed isn't really about light, and it's not really about gravity. It's about the maximum rate at which cause and effect can propagate through the universe. Dr. Sean Carroll at Johns Hopkins University explains it beautifully. The speed of light should really be called the speed of causality. It's the speed at which changes in the universe can influence other parts of the universe. Whether those changes are electromagnetic, gravitational, or something else entirely, They all respect this cosmic speed limit because it's built into the fabric of space-time itself. This universal speed limit preserves causality and prevents paradoxes. If gravity could travel faster than light, you could potentially send signals into your own past, creating grandfather paradoxes and logical contradictions. The fact that gravity obeys the same speed limit as light ensures that cause always precedes effect, maintaining the logical consistency of the universe. To truly understand why the speed of gravity matters so profoundly, we need to examine one of the greatest intellectual battles in the history of science: the fundamental disagreement between Newton's instantaneous gravity and Einstein's speed-limited gravity. This wasn't just a minor technical dispute, it was a clash between two completely different visions of reality that would take centuries to resolve and would ultimately revolutionize our understanding of space, time, and the cosmos itself. Isaac Newton's law of universal gravitation, published in his Principia Mathematica in 1687, was one of humanity's greatest intellectual achievements. For the first time, someone had discovered a mathematical law that governed both earthly and celestial phenomena. The same force that causes an apple to fall from a tree also keeps the moon in orbit around Earth and Earth in orbit around the Sun. This was a stunning unification that transformed our view of the universe. Newton's equation was elegantly simple. The gravitational force between two objects equals the gravitational constant times their masses divided by the square of the distance between them. Using this formula, astronomers could predict eclipses centuries in advance, calculate the orbits of comets, and even discover new planets. When Urbain Le Verrier used Newton's laws to predict the existence and location of Neptune in 1846, it seemed to confirm that Newton had discovered the true law of gravity. But Newton's gravity had a troubling feature that bothered even Newton himself. According to his equations, gravity acts instantaneously across any distance. If you moved a mass here, another mass there would immediately feel the change, no matter how far apart they were. This action at a distance seemed almost magical. How could one object influence another across millions of miles of empty space with no time delay? Newton himself was uncomfortable with this aspect of his theory. In a letter to Richard Bentley in 1693, he wrote that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, without the mediation of anything else, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Yet despite this philosophical discomfort, Newton's equations worked so well that scientists accepted instantaneous gravity as a fact of nature. For over 2 centuries, every calculation, every prediction, every astronomical observation seemed to confirm that gravity acted instantly. The success was so complete that by the late 1800s, many physicists believed that Newton's laws, along with Maxwell's equations for electromagnetism, had essentially completed physics. But cracks were beginning to show. The most famous was the precession of Mercury's perihelion. Mercury's elliptical orbit slowly rotates around the Sun, and most of this precession could be explained by the gravitational pull of other planets. But there was a tiny discrepancy, 43 arcseconds per century, that couldn't be explained by Newton's laws. Astronomers searched for an undiscovered planet called Vulcan orbiting closer to the Sun, but it didn't exist. Enter Albert Einstein, who in 1905 had already revolutionized physics with special relativity, showing that space and time were interconnected and that nothing could travel faster than light. But special relativity only dealt with objects moving at constant velocities. Einstein spent the next decade working on a theory that could handle acceleration and gravity, finally publishing General Relativity in 1915. Einstein's insight was profound. gravity isn't a force at all. Instead, massive objects bend the fabric of space-time, and objects move along the straightest possible paths through this curved geometry. John Wheeler later summarized it perfectly. Matter tells space-time how to curve, and curved space-time tells matter how to move. But crucially, in Einstein's theory, changes in the gravitational field don't propagate instantaneously. Instead, they ripple outward at exactly the speed of light. If you suddenly moved a massive object, the change in space-time curvature would spread outward like a wave, reaching distant objects only after a delay determined by the speed of light. This created a dramatic difference between Newton and Einstein's predictions. In Newton's universe, if the sun suddenly vanished, Earth would immediately fly off in a straight line. In Einstein's universe, Earth would continue orbiting the non-existent sun for 8 minutes and 20 seconds until the gravitational change reached us at light speed. We would see the sun disappear and feel the loss of its gravity at exactly the same moment. Einstein's theory immediately solved the Mercury perihelion problem. The extra precession was caused by the curvature of spacetime near the sun, an effect not present in Newton's theory. When Einstein calculated this effect and found it exactly matched the observed 43 arcseconds per century, he later recalled that he had heart palpitations from excitement. He knew he had discovered something profound. Dr. Peter Gallison at Harvard University, who has studied this period extensively, notes, "This wasn't just a correction to Newton, it was a complete reconceptualization of what gravity is. Newton gave us forces acting instantly across space. Einstein gave us the geometry of space-time itself, with changes propagating at a finite speed." The implications were staggering. If gravity travels at light speed, then the gravitational pull we feel from distant objects is always outdated. We feel the moon's gravity from where it was 1.3 seconds ago. We feel Jupiter's gravity from where it was about 40 minutes ago when we're at closest approach. For distant galaxies, we feel gravitational effects from where they were millions or billions of years ago. This might seem like it would cause chaos in orbital mechanics, but general relativity handles it elegantly. The theory includes subtle effects called gravitational aberration and retardation that exactly compensate for the finite speed of gravity, keeping orbits stable. It's as if the universe has built-in error correction for the time delays caused by gravity's finite speed. Dr. Steve Carlip at UC Davis, who has studied this extensively, explains, "It seems almost miraculous, but the equations of general relativity automatically account for the finite speed of gravity in just the right way to keep planetary orbits stable. If gravity traveled at any other speed, faster or slower than light, orbits would spiral in or out. The fact that gravity travels at exactly light speed is what keeps the solar system stable." The first experimental hints that Einstein might be right came from observations of binary star systems. If gravity traveled instantaneously, binary stars should orbit stably forever. But if gravitational changes propagate at light speed, the systems should lose energy to gravitational waves and slowly spiral together. Observations showed that binary star orbits were indeed decaying, though the measurements weren't precise enough to definitively confirm Einstein's predictions. The real breakthrough came with the discovery of the Hulse-Taylor binary pulsar in 1974. This system consisted of two neutron stars orbiting each other every 7.75 hours. One of them was a pulsar, emitting regular radio pulses that could be timed with extraordinary precision. Over years of observations, Taylor and his colleagues showed that the orbit was decaying at exactly the rate Einstein predicted if gravitational waves were carrying away energy at light speed. Dr. Joseph Taylor, in his Nobel Prize lecture, said, "For the first time, we had indirect but compelling evidence that gravitational waves exist and that they travel at the speed of light, just as Einstein predicted. Newton's instantaneous gravity was finally ruled out by observation." But indirect evidence wasn't enough for many scientists. They wanted direct detection of gravitational waves and direct measurement of their speed. This would require detecting the incredibly tiny distortions of spacetime caused by passing gravitational waves, a challenge that seemed impossible for decades. The LIGO project, conceived in the 1970s and built over decades with over $1 billion in funding, was humanity's attempt to directly detect these space-time ripples. Many scientists were skeptical it would work. The required precision seemed beyond human capability. Yet on September 14, 2015, LIGO succeeded, detecting gravitational waves from colliding black holes and opening a new window on the universe. While we've definitively proven that gravity travels at the speed of light in the realm of general relativity, there's a deeper mystery that keeps physicists awake at night. What happens to gravity at the quantum scale? You see, our two most successful theories of the universe, general relativity and quantum mechanics, are fundamentally incompatible. And hidden within this incompatibility might be surprises about gravity's speed that could revolutionize our understanding of reality once again. At the scales we can currently measure, from subatomic particles to galaxy clusters, gravity obeys Einstein's speed limit perfectly. But at the Planck scale, distances of 10 to the negative 35 meters and times of 10 to the negative 43 seconds, our theories break down completely. Here, quantum effects and gravity become equally important, and we enter the realm of quantum gravity, where the speed of gravitational influences might behave in ways we haven't imagined. Dr. Wu. Carlo Rovelli at the Centre de Physique Théorique in France, one of the founders of loop quantum gravity, explains the profound challenge. At the Planck scale, spacetime itself might not be smooth, but made of discrete units like pixels in a photograph. If space and time are quantized, then our whole concept of speed, including the speed of gravity, might need to be reconsidered. Loop quantum gravity predicts that spacetime has a granular structure at the smallest scales. In this theory, space isn't continuous but made of tiny loops woven together like fabric. Time doesn't flow smoothly, but ticks forward in discrete steps. If this is true, gravitational effects might propagate through these quantum loops in ways that appear to violate or modify the speed of light at microscopic scales, while still appearing to obey it at larger scales. String theory, the other major candidate for quantum gravity, offers even stranger possibilities. In string theory, gravity is caused by closed loops of vibrating strings moving through multiple dimensions, perhaps 10 or 11 in total. The gravitons that carry gravitational force in this theory are closed strings that can move through all dimensions, while other particles are open strings confined to our three-dimensional brain. Dr. Juan Maldacena at the Institute for Advanced Study has shown through his ADS CFT correspondence that gravity in higher dimensions can be mathematically equivalent to quantum field theory in lower dimensions. This suggests that what we perceive as gravitational effects traveling at light speed might be shadows of something more fundamental happening in higher dimensions, where our usual concepts of distance and speed might not apply. Recent experiments have begun probing whether the speed of gravity might vary at different energy scales. The LIGO and Virgo collaborations have looked for frequency-dependent variations in gravitational wave speed. If quantum gravity effects exist, higher frequency gravitational waves might travel at slightly different speeds than lower frequency ones. So far, no variations have been detected constraining any quantum gravity effects to incredibly small scales. Dr. Giovanni Amelino Camiglia at Sapienza University of Rome has proposed that quantum gravity might create a rainbow effect where different energies of gravitational waves travel at slightly different speeds, similar to how light disperses in a prism. His calculations suggest these effects would be tiny, perhaps 1 part in 10 to the 20th, but potentially detectable with future, more sensitive gravitational wave detectors. The implications extend beyond pure physics. If gravity's speed varies even slightly at quantum scales, it could affect our understanding of the early universe. In the first fraction of a second after the Big Bang, when quantum gravity effects were important, gravitational influences might have propagated differently than they do today. This could impact theories of cosmic inflation, the formation of the first structures, and even the nature of the Big Bang itself. Speaking of cosmic speed limits and their implications, if you've ever wondered what would happen if we could actually break these fundamental barriers, I talk about that in the video called "What Would Really Happen If We Traveled Faster Than Light?" We explore how faster-than-light travel would transform space exploration, time, and the future of humanity. Learn about Einstein's relativity, warp drives, tachyons, and the real physics behind light speed. Check it out after this video. The link is in the description and on the card above. Now back to our journey. Dr. Abhay Ashtekar at Penn State, another founder of Loop Quantum Gravity, has developed models where the Big Bang wasn't a beginning, but a big bounce. A transition from a previously contracting universe. In these models, quantum gravity effects prevent the singularity that general relativity predicts, and the speed of gravitational influences might have been different during the bounce phase. Dark matter and dark energy add another layer to the mystery. These invisible components make up 95% of the universe, yet we don't understand what they are or how they interact gravitationally. Some theories propose that dark matter might interact through a fifth force that propagates at a different speed than ordinary gravity. Others suggest that dark energy might modify how gravitational effects propagate across cosmic distances. Dr. Claudia de Rham at Imperial College London has developed theories of massive gravity, where gravitons have a tiny but non-zero mass. If gravitons have mass, they would travel slightly slower than light, though the difference would be incredibly small, perhaps 1 part in 10 to the 32nd. Current observations from LIGO and pulsar timing constrain the graviton mass to be less than 10 to the negative 23 electron volts. Incredibly tiny, but potentially non-zero. The recent detection of gravitational waves from neutron star mergers has provided the strongest constraints yet on alternative theories of gravity. The fact that gravitational waves and electromagnetic waves from GW 170817 arrived within 1.7 seconds after traveling 130 million years rules out many modified gravity theories. But some theories remain viable, predicting effects that would only show up at shorter distances or higher energies. Dr. Rana Adhikari at Caltech, who works on LIGO detector technology, envisions future detectors that could probe quantum gravity directly. We're designing detectors that could see gravitational waves from the very early universe, perhaps even from the Planck epoch. These primordial gravitational waves might carry signatures of quantum gravity effects, including variations in propagation speed that could tell us about the fundamental nature of spacetime. Emergent gravity theories propose something even more radical, that gravity isn't fundamental but emerges from more basic quantum information processes. Dr. Erik Verlinde at the University of Amsterdam has developed a theory where gravity arises from changes in quantum entanglement entropy. In this view, what we perceive as gravitational effects traveling at light speed might be information propagating through quantum entanglement networks. These ideas connect to the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary. If reality is fundamentally holographic, then gravitational effects in the bulk might be instantaneous from one perspective while appearing to travel at light speed from another. It's as if the universe maintains multiple consistent descriptions of the same events. Dr. Leonard Susskind at Stanford, one of the fathers of the holographic principle, suggests that quantum entanglement and wormholes might be the same phenomenon viewed from different perspectives, a conjecture known as ER-EPR. If true, this would mean that what we see as gravity traveling at light speed through normal space might sometimes take shortcuts through quantum entanglement, appearing to violate the speed limit while actually respecting it in a deeper sense. Laboratory experiments are beginning to probe these exotic possibilities. Scientists at the University of Vienna have conducted experiments showing that gravity affects quantum superposition, while researchers at University College London are planning experiments to put large molecules in quantum superposition to test how gravity behaves at quantum scales. The implications for technology, while speculative, are tantalizing. If we could manipulate quantum gravity effects, we might be able to create regions where gravitational influences propagate differently, potentially enabling exotic technologies like warp drives or traversable wormholes. While these remain in the realm of science fiction for now, our growing understanding of quantum gravity might reveal loopholes in what seems like an absolute cosmic speed limit. Dr. Kip Thorne, who won the Nobel Prize for his work on gravitational waves, remains cautiously optimistic. Every time we've thought we understood the fundamental laws of physics, nature has surprised us. The speed of gravity seems absolute in general relativity, but quantum gravity might reveal subtleties we haven't imagined. The universe is almost certainly stranger than we currently suppose. Now that we know gravity travels at exactly the speed of light, let's explore what this means for the grand architecture of the universe itself. This isn't just an abstract fact for physicists to ponder. It fundamentally shapes everything from the stability of planetary orbits to the fate of the cosmos. The finite speed of gravity creates a cosmic choreography where past, present, and future are interwoven in ways that challenge our deepest intuitions about reality. Consider what's happening right now as Earth orbits the Sun. The gravitational pull you feel isn't from where the Sun is at this moment, but from where it was 8 minutes and 20 seconds ago. Similarly, the Sun feels Earth's gravity from where our planet was 8 minutes and 20 seconds in the past. This might seem like it should cause chaos. How can stable orbits exist when everything is pulling on outdated positions? The answer reveals the elegant mathematical beauty of Einstein's general relativity. Dr. Steve Carlip at the University of California, Davis has spent years studying this apparent paradox. It seems almost miraculous, he explains, but general relativity includes subtle, velocity-dependent terms that exactly compensate for the time delay. When Earth pulls on the Sun's 8-minute-old position, there are additional forces that depend on the Sun's velocity that perfectly correct for the delay. It's as if the universe has built-in error correction for gravitational time lags. This compensation isn't approximate, it's exact to the level we can measure. The Lunar Laser Ranging Experiment, which bounces laser beams off mirrors left on the Moon by Apollo astronauts, has tested this to extraordinary precision. After more than 50 years of measurements accurate to millimeters, the Moon's orbit shows no signs of the instability that would occur if gravity traveled at any speed other than light speed. But the implications go far beyond our solar system. In binary star systems throughout the galaxy, the finite speed of gravity causes energy to be radiated away as gravitational waves. This energy loss causes the stars to slowly spiral together, eventually merging in cataclysmic events. The Hulse-Taylor pulsar, monitored for over 40 years, has lost exactly the amount of energy predicted by gravitational radiation traveling at light speed, a discovery that earned the 1993 Nobel Prize in Physics. Dr. Alessandra Buonanno at the Max Planck Institute for Gravitational Physics, who develops the theoretical models used to analyze LIGO data, describes the cosmic dance. Every accelerating mass in the universe creates gravitational waves that ripple outward at light speed. From binary stars to orbiting planets to the vibrations of a tuning fork, everything contributes to a cosmic symphony of space-time ripples. Most are too weak to detect, but they're all there, carrying information about their sources across the universe. The finite speed of gravity also explains one of the most profound features of our universe: why it looks the same in all directions. If gravity traveled infinitely fast, different regions of the early universe could have communicated and equalized instantaneously, but this would have left observable traces that we don't see. The fact that gravity obeys the cosmic speed limit means that in the early universe, regions separated by more than the light travel distance couldn't influence each other, leading to the nearly perfect uniformity we observe in the cosmic microwave background. This connects to cosmic inflation, the period of exponential expansion in the universe's first fraction of a second. Dr. Alan Guth at MIT, who proposed inflation, notes that the finite speed of gravity is crucial for inflation to work. If gravitational effects could propagate faster than light, inflation couldn't have smoothed out the universe in the way we observe. The speed of gravity isn't just a detail, it's fundamental to why the universe looks the way it does. The speed of gravity even affects the universe's ultimate fate. Dark energy is causing cosmic expansion to accelerate, and because gravity travels at light speed, there's a cosmic event horizon beyond which we can never receive gravitational influences. Galaxies beyond this horizon are causally disconnected from us forever. Dr. Lawrence Krauss at Arizona State University calculates that in about 100 billion years, all galaxies beyond our local group will have passed beyond this gravitational horizon, leaving us in an island universe surrounded by darkness. But perhaps nowhere is the finite speed of gravity more important than in black hole physics. When matter falls into a black hole, the change in the gravitational field propagates outward at light speed. This creates fascinating effects near the event horizon. From the perspective of an outside observer, gravitational effects from infalling matter appear to freeze at the horizon, creating what some physicists call a frozen star appearance. Dr. A. Andrew Hamilton at the University of Colorado, who creates visualizations of black hole physics, explains, as you approach a black hole, the finite speed of gravity creates layers of gravitational influence from matter that fell in at different times. It's like geological strata, but made of frozen gravitational fields. The entire history of everything that ever fell into the black hole is encoded in the gravitational field just outside the event horizon. This has profound implications for the black hole information paradox. If information can't travel faster than light, and gravity travels at light speed, then information falling into a black hole can't simply disappear. It must be preserved somehow in the gravitational field. Recent work by Dr. Ahmed Almhairi and colleagues suggests that this information might be encoded in subtle correlations in the gravitational field that we're only beginning to understand. The finite speed of gravity also constrains possible modifications to Einstein's theory. Any theory of quantum gravity must respect this speed limit or explain why it appears so exact at the scales we can measure. Dr. Cliff Burgess at McMaster University, who works on effective field theory approaches to gravity, notes, The fact that gravity travels at exactly light speed, not even slightly faster or slower, is a powerful constraint on beyond Einstein theories. It's like a cosmic quality control stamp that any new theory must match. Gravitational lensing provides another window into gravity's finite speed. When light from a distant galaxy passes near a massive object, the gravitational field bends its path. But because gravity travels at light speed, the lensing we see is from where the massive object was when the light passed by, not where it is now. For rapidly moving lenses, this creates time delay effects that astronomers are just beginning to exploit. Dr. Sherry Suyu at the Max Planck Institute for Astrophysics uses gravitational lensing time delays to measure cosmic expansion. When a distant quasar is lensed by a galaxy, we see multiple images that travel different paths. Because gravity travels at light speed, these paths have different lengths and different time delays. By measuring these delays, we can map the gravitational field and measure cosmic distances independently of other methods. The speed of gravity even affects the search for dark matter. If dark matter particles interact gravitationally, those interactions propagate at light speed. This constrains models of dark matter and affects how dark matter structures form. Dr. Lisa Randall at Harvard has proposed that dark matter might interact through forces that propagate at different speeds, which could explain some puzzling observations about galaxy formation. Pulsar timing arrays like nanograv use the finite speed of gravity to detect gravitational waves with wavelengths of light years. As these waves pass by, they slightly change the arrival times of pulsar signals. Because the waves travel at light speed, pulsars in different directions show correlated timing, changes with specific delays. Dr. Maura McLaughlin at West Virginia University describes it as using the entire galaxy as a gravitational wave detector, with the speed of light providing our timing reference. The philosophical implications are equally profound. The finite speed of gravity means that gravitational influences, like electromagnetic ones, are always about the past. We never experience the universe as it is now. In any absolute sense, everything we see and feel is information from the past, arriving at light speed. This reinforces Einstein's revelation that simultaneity is relative and that past, present, and future are more fluid than our everyday experience suggests. Dr. Sean Carroll at Johns Hopkins University reflects on the deeper meaning. The fact that gravity travels at light speed tells us something profound about the nature of spacetime. It's not just a stage where events happen, it's a dynamic, communicating entity where changes propagate at a finite speed. This speed limit isn't a restriction, it's what makes causality possible and gives the universe its ordered structure. Looking to the future, the finite speed of gravity will be crucial for multi-messenger astronomy. When LIGO detects gravitational waves from a cosmic event, astronomers know that electromagnetic signals are traveling alongside at the same speed. This allows coordinated observations that would be impossible if the speeds were different. The next generation of detectors will exploit this correspondence to probe ever more exotic phenomena. We stand at the dawn of a new era in astronomy where the speed of gravity isn't just a theoretical concept but a practical tool for exploring the universe. The confirmation that gravity travels at light speed has opened up possibilities that would have seemed like science fiction just decades ago. From detecting invisible black hole collisions billions of light years away to potentially discovering new physics beyond Einstein, the future of gravitational astronomy promises revelations that will reshape our understanding of reality itself. The next generation of gravitational wave detectors will push our ability to measure gravity's speed to unprecedented precision. The Einstein telescope, planned for construction in Europe, will be 10 times more sensitive than current detectors. built underground to reduce seismic noise with arms 10 kilometers long instead of 4, and using advanced quantum techniques to reduce noise, it will detect gravitational waves from the entire observable universe. Michele Maggiore at the University of Geneva, who leads theoretical studies for the Einstein telescope, explains the transformative potential. We'll go from detecting a few events per year to thousands per day. Every black hole merger, every neutron-star collision in the observable universe will be visible to us. We'll measure the speed of gravity with such precision that even tiny deviations predicted by quantum gravity theories could be detectable. The Cosmic Explorer, proposed for construction in the United States, will have arms 40 kilometers long, 10 times longer than LIGO. This increased size, combined with new technologies like squeezed light and cryogenic cooling, will allow it to peer back to the cosmic dawn when the first black holes formed. By comparing arrival times of gravitational waves from these ancient events with any electromagnetic counterparts, we'll test whether gravity's speed has remained constant over cosmic time. But the most ambitious project is LISA, the Laser Interferometer Space Antenna. Scheduled for launch in the 2030s, LISA will consist of 3 spacecraft separated by 2.5 million kilometers, forming a triangle in space that follows Earth's orbit around the Sun. Free from Earth's seismic noise and with arms millions of times longer than ground-based detectors, LISA will detect lower-frequency gravitational waves from supermassive black hole mergers. Dr. Carsten Dansman at the Max Planck Institute for Gravitational Physics, who leads LISA development, describes its revolutionary capabilities. LISA will see gravitational waves from black holes millions of times the Sun's mass spiraling together in distant galaxies. We'll detect these events years before they merge, allowing us to predict exactly when and where to point electromagnetic telescopes. This will test gravity's speed across billions of years of cosmic time with extraordinary precision. The implications for testing fundamental physics are staggering. If gravity's speed varies even slightly with energy or distance, as some quantum gravity theories predict, LISA will detect it. By observing gravitational waves of different frequencies traveling billions of light-years, we can search for the dispersion effects that would indicate a breakdown of Einstein's theory at extreme scales. Pulsar timing arrays are already revolutionizing our understanding of low-frequency gravitational waves. The Nanograv collaboration recently announced evidence for a gravitational wave background, a cosmic hum from millions of supermassive black hole pairs slowly spiraling together throughout the universe. As these arrays become more sensitive, they'll provide another independent measurement of gravity's speed on galactic scales. Dr. Xavier Siemens at Oregon State University, who leads Nanograv's gravitational wave searches, explains, "We're using millisecond pulsars as cosmic clocks spread across the galaxy. When gravitational waves pass by, they create correlated timing changes that depend on the wave's speed. We can measure gravity's speed independently of LIGO and with completely different sources, supermassive black holes instead of stellar mass ones. The Square Kilometre Array, SKA, under construction in Australia and South Africa, will monitor thousands of pulsars with unprecedented precision. By timing these cosmic clocks for decades, SKA will measure gravity's speed using gravitational waves with wavelengths of light years, scales where some theories predict deviations from light speed might appear. But perhaps the most exciting possibility is detecting primordial gravitational waves from the Big Bang itself. These waves, produced in the universe's first fraction of a second, would carry information from when the fundamental forces were unified and quantum gravity effects were important. If gravity's speed was different in the early universe, these primordial waves would bear the signature. Dr. Mark Kamiankowski at Johns Hopkins University, who studies primordial gravitational waves, notes, The early universe was a natural particle accelerator, reaching energies we'll never achieve in laboratories. Gravitational waves from inflation would tell us about physics at the Planck scale. If gravity's speed varied then, we'd see it in the polarization patterns of the cosmic microwave background. Future cosmic microwave background experiments like CMB-S4 and the Simons Observatory will search for these primordial gravitational wave signatures with sensitivity far exceeding current instruments. By measuring how these ancient waves propagated across the universe, we'll test whether gravity has always traveled at light speed or if the cosmic speed limit itself has evolved. The technological innovations driven by gravitational wave astronomy are already transforming other fields. The quantum noise reduction techniques developed for LIGO are being applied to quantum computing and precision measurement. The ultra-stable lasers and vibration isolation systems have applications in everything from telecommunications to manufacturing. Dr. Nergis Mavalvala at MIT, who pioneered quantum squeezing techniques for LIGO, describes the broader impact. In pushing to measure gravity's speed with ever greater precision, we're developing technologies that transform our ability to measure and control the quantum world. The same techniques that let us detect space-time ripples smaller than an atomic nucleus are enabling new quantum technologies. Artificial intelligence and machine learning are becoming crucial tools for gravitational wave astronomy. Neural networks can identify gravitational wave signals in noisy data faster than traditional methods, and AI algorithms can predict waveforms for black hole mergers that would take supercomputers weeks to calculate. As detectors become more sensitive and detect thousands of events, AI will be essential for real-time analysis. Dr. Gabriela Gonzalez at Louisiana State University, former spokesperson for LIGO, envisions the future. We're moving from individual detections to population studies. Instead of measuring gravity's speed from one event, we'll use thousands of events to map how gravity behaves across different scales, energies, and cosmic epochs. It's like going from studying individual stars to understanding entire galaxies. The multi-messenger astronomy enabled by gravity traveling at light speed is transforming our understanding of cosmic events. When gravitational waves and light arrive together, we get a complete picture impossible with either alone. The neutron-star merger GW1 70817 taught us about heavy element creation, gamma-ray burst mechanisms, and the expansion rate of the universe, all from one event. Future detectors will extend multi-messenger astronomy to new realms. When LISA detects merging supermassive black holes, ground-based telescopes will search for electromagnetic counterparts from surrounding gas. When the Einstein telescope detects black holes forming from collapsing stars, neutrino detectors will look for associated neutrino bursts. Each messenger traveling at its characteristic speed, gravity and light at c, massive neutrinos, slightly slower, will reveal different aspects of cosmic catastrophes. Dr. Samaya Nisanke at the University of Amsterdam, who specializes in multi-messenger astronomy, describes the future. We're building a network of cosmic sensors that will work together to decode the universe's most extreme events. The fact that gravity travels at light speed is the Rosetta Stone that lets us coordinate these observations and extract maximum science from each event. The search for deviations from light speed continues with ever more creative approaches. Some scientists propose using gravitational lensing of gravitational waves, where a massive object bends passing gravitational waves just as it bends light. By comparing the lensing of gravitational waves and light from the same source, we could detect any difference in propagation speed with extraordinary precision. Others suggest looking for echoes in gravitational wave signals that might indicate exotic compact objects that aren't quite black holes. If gravity's speed varies near the extreme space-time curvature of almost black holes, It would create distinctive echo patterns in the gravitational wave signal. Several groups have searched for such echoes, so far without success, but future detectors will probe this possibility more deeply. The implications extend beyond pure science. As we develop global networks of gravitational wave detectors, we're creating a new kind of international scientific collaboration. Data must be shared instantly, analyses coordinated across continents, and discoveries announced simultaneously worldwide. The speed of gravity has become a unifying principle for global scientific cooperation. Right now, as you sit reading this, your gravitational field is radiating outward at 300,000 kilometers per second. The gravitational influence of your body is reaching the Moon in just over a second, Mars in a few minutes, and the nearest stars in years. Incredibly faint, yes, but real and measurable in principle. You are not separate from the cosmic gravitational web. You are a node within it, both receiving and transmitting gravitational information at the universal speed limit. Dr. Brian Greene at Columbia University puts this in perspective. Every time you move, you create gravitational waves. When you wave your hand, you're sending ripples through space-time that propagate outward at light speed. These waves are unimaginably weak, far too small for any conceivable detector, but they're real. You are literally broadcasting your movements to the universe. This isn't just poetic metaphor, it's physical reality. The LIGO detectors that confirmed gravity travels at light speed work on the same principle, just with much more massive objects. When black holes spiral together billions of light years away, they create gravitational waves strong enough for us to detect. When you move, you create the same kinds of waves, just quintillions of times weaker. The physics is identical, only the scale differs. Consider what this means for your connection to the cosmos. The gravitational waves from your birth are still traveling outward, having now reached stars about as many light years away as your age. Every significant movement of your life, your first steps, every embrace, every dance, has sent gravitational ripples expanding into space. In a very real sense, the universe contains a gravitational record of your existence spreading outward at light speed. But you're not just a transmitter of gravitational waves, you're also a receiver. Your body responds to the gravitational fields of everything around you, from the Earth beneath your feet to the Moon in the sky to distant galaxies. The tides in Earth's oceans that respond to lunar gravity have microscopic counterparts in your own body. You are gravitationally connected to everything, with those connections propagating at light speed. Dr. Jana Levin at Barnard College, author of Black Hole Survival Guide, reflects on this cosmic connection. We tend to think of ourselves as separate from the universe, but gravity tells a different story. We're woven into space-time itself, each of us creating and responding to the gravitational fabric. The confirmation that gravity travels at light speed means we're all part of a cosmic network where information about matter and energy flows at the maximum possible rate. The finite speed of gravity also shapes your everyday experience in subtle ways. The Earth you're standing on is pulling you toward where it was about 8 microseconds ago, the time it takes gravity to travel from Earth's center to the surface. This delay is utterly negligible for daily life, but it's real. Even the gravitational pull between you and nearby objects involves these tiny, light-speed delays. More profoundly, the speed of gravity determines the structure of the universe you inhabit. If gravity traveled faster than light, the cosmos would be fundamentally different. Planets might not have stable orbits, stars might not form properly. The delicate balance of forces that allows atoms, molecules, and life to exist depends critically on gravity respecting the cosmic speed limit. You exist because gravity travels at exactly light speed, not faster or slower. Dr. Lisa Randall at Harvard University emphasizes this cosmic fine-tuning. The fact that gravity travels at light speed isn't just a random parameter, it's essential for a universe that can support complexity and life. A universe with instantaneous gravity would be radically different, probably unable to support the kinds of structures we see. We exist because the universe's fundamental forces respect this speed limit. Your generation is witnessing humanity's first direct measurements of gravitational waves, confirming that gravity indeed travels at light speed. This isn't just an abstract scientific achievement, it's a milestone in human consciousness. For the first time in history, we can sense space-time ripples from across the universe. We've gained a new sense, as revolutionary as sight or hearing, but one that perceives the fabric of reality itself. Think about what this means. When LIGO detected the collision of black holes over 1 billion light-years away, humanity felt the universe tremble. Those gravitational waves passed through you, slightly stretching and squeezing every atom in your body. The effect was unimaginably small, far too tiny to consciously perceive, but it was real. You were physically touched by an event that happened before multicellular life existed on Earth. Dr. Kip Thorne, who spent decades working toward gravitational wave detection, describes the profound implications. We've opened a new window on the universe. Future generations will look back on this moment as the beginning of gravitational wave astronomy. And knowing that these waves travel at light speed gives us a precise tool for exploring the cosmos in ways we're only beginning to imagine. The philosophical implications run even deeper. The finite speed of gravity means that gravitational causality, like electromagnetic causality, is limited by light speed. Your gravitational influence on distant objects is always delayed, just as your visual perception of them is delayed. This reinforces Einstein's insight that there is no absolute now, simultaneity is relative, and the present moment is a local, not universal concept. This has profound implications for free will and determinism. Because gravitational influences propagate at finite speed, the future isn't entirely determined by the present state of the universe. There's always a horizon beyond which current conditions can't yet have causal influence. In a universe with instantaneous gravity, the future might be completely determined. But with gravity limited to light speed, there's room for genuine novelty and emergence. Dr. Paul Davies at Arizona State University explores these deep questions. The finite speed of gravity is intimately connected to the nature of time and causality. It ensures that the future remains open, that information takes time to propagate, that cause and effect maintain their proper relationship. It's part of what makes the universe comprehensible and allows for the emergence of complexity and consciousness. As you go forward from this moment, carry with you the knowledge that you're part of this cosmic gravitational network. When you look at the stars, remember that their gravity is reaching you at light speed, just as your gravity reaches toward them. When you feel the Earth's pull, know that it travels to you at the same cosmic speed limit that governs black holes and galaxies. The next time you hear about a gravitational wave detection, remember that those waves pass through you. You are part of the measurement, a tiny component of the vast detector that is Earth itself. Your atoms stretched and squeezed in response to distant cosmic events, making you a participant in the universe's gravitational symphony. Dr. Nergis Mavalvala at MIT, who helped develop the technology to detect gravitational waves, offers this perspective. Every human being is a gravitational wave detector, just not a very sensitive one, but the waves pass through all of us. We're all connected to the cosmos through these ripples in space-time. Knowing they travel at light speed tells us we're part of a universe where everything is connected but nothing is instantaneous. The future holds even more amazing possibilities. As gravitational wave detectors become more sensitive, we'll map the universe in gravitational waves just as we've mapped it in light. We'll detect the gravitational echoes of the Big Bang itself. We might even discover new phenomena that challenge our understanding of gravity's speed in ways we can't yet imagine. You are living in the first generation of humans who know with certainty that gravity travels at light speed. This knowledge transforms our understanding of everything from black holes to the Big Bang, from the stability of atoms to the fate of the universe. But most importantly, it reveals your deep connection to the cosmos. You are made of atoms, forged in stars, held together by forces that propagate at light speed, embedded in a space-time fabric that ripples with gravitational waves. Every movement you make sends these ripples outward at light speed, adding your unique signature to the cosmic gravitational symphony. You are not just in the universe. You are part of its fundamental structure, a conscious being woven into the very fabric of space-time. This is your cosmic heritage, to be part of a universe where gravity travels at light speed, binding everything together while respecting the cosmic speed limit that makes causality, complexity, and consciousness possible. In understanding the speed of gravity, you understand something fundamental about your own existence and your eternal connection to the cosmos. The universe speaks in gravitational waves traveling at light speed, and now, for the first time in cosmic history, it has evolved conscious beings who can listen. You are the universe understanding itself, measuring its own fundamental properties, and marveling at the elegant laws that make existence possible. This is your moment, your revelation, your connection to the infinite cosmos that surrounds and includes you. If you made it this far, make sure to subscribe and give a like to this video. And if you enjoyed this video, I am sure you will love this other on the screen. Why light has a speed limit. If you're fascinated by relativity, quantum physics, and the deepest questions in science, this is the ultimate guide to why light speed is the universe's ultimate limit. See you there.